Okay, so last time we started discussing about minimal polynomials. So today we'll continue a little bit about minimal polynomials, and towards the end I'll start the discussion on Jordan forms. Yeah. So remember the definition. So if you have a polynomial, if you have a matrix A, then a monic polynomial Px with coefficient in, so a priori it looks like, with coefficient, so say coefficient of this matrix are in the field F, then a monic polynomial with coefficient in F is said to be minimal polynomial of A over F if a priori it seems like it's defined over F, but as I said, monic polynomial is unique, right? So eventually you'll see that any field containing F is going to be containing the coefficients of A, it's the same polynomial. Yeah. So it's defined to be uh, uh, such a monic polynomial such that PA is 0 and this polynomial has the least degree with this property. Yeah. So it's a monic polynomial of least degree such that PA is 0. Okay, that is called the minimal polynomial. That is called the minimal polynomial of it. And then Cayley-Hamilton theorem told us that this exists, yeah, because by Cayley-Hamilton theorem, this set S, which is set of all monic polynomials such that Fa is 0, is non-empty, right? Characteristic polynomial belongs there. Yeah, this is what Cayley-Hamilton theorem told us, that if you plug in the matrix A in the characteristic polynomial of A, then we get 0. The 0 endomorphism. Right, so this is non-empty, and hence you can so you take Px to be the polynomial of least degree in S. Then Px is by definition the minimal polynomial of A. Yeah, no smaller degree polynomial, monic polynomial will satisfy A. Okay, so I've already written the minimal polynomial of A, but maybe one has to prove the uniqueness. Yeah. So in fact, we'll prove something stronger. So let Px be a minimal polynomial of a square matrix A over F. Let Gx be any polynomial with coefficient in F such that Ga is 0. Then we will show that Px divides Gx. Yeah. So in other words, minimal polynomial divides every element of the set S, which we have written. Yeah, that is what this statement says. Okay, makes sense, everyone? I can't see your video, so I don't. Yes. And suddenly something went wrong. Now I can see your video. But this has. Oh, okay. Good that I write a little bit, otherwise this will go for hours. Yeah. Okay. Yeah, you can see again, right, the screen? Yes, sir. Okay. Yeah, so the Cayley-Hamilton theorem implies that yeah, so this is, yeah, so we will prove this. Yeah, so if we have this minimal polynomial, if Px is the minimal polynomial of a matrix A, then it divides every polynomial which satisfy such that G of A is 0. Yeah. So this is not difficult. You just use the division algorithm, right? So you know what division algorithm is, right? You try to divide Gx by Px, and you get a division algorithm or remainders theorem. I don't know. So maybe it's also known as remainders theorem. So let's say remainders theorem. So you know this, right? That if you divide the polynomial Gx by Px, then you'll get a quotient and a remainder polynomial. and the remainder polynomial will have degree less than the degree of the one with which you are dividing. And that means degree of px. Okay, or remainder polynomial will be 0. Is this okay? The remainders theorem? Yeah. So we apply this remainders theorem and then we plug in a. Yeah. So we evaluate. We do this transformation. We plug in a. So of course, GA is going to be same as I mean both the left and right hand side polynomial are same. So if you plug in a, we get the equality of the endomorphism. So GA is same as QA times PA plus RA, which implies, so remember GA is 0 by hypothesis, right? And PA is 0. And if you multiply any matrix by the 0 matrix, you get 0. So that tells you that RA is also 0. Yeah. But Rx has degree less than Px, right? If it is non-zero. But that's not possible because so here we are using that Px is minimal. Is minimal polynomial is minimal polynomial of A. Yeah. So you can't have a smaller degree polynomial with which satisfies A. Yeah, which is satisfied by A. So Rx must be 0, which precisely means that Px divides Gx. Yeah. Okay, and as a consequence, we see that minimal polynomial is unique, right? Because I mean, if there is another polynomial of the same degree, then it has to divide. So, so say let Px and Gx be minimal polynomial of A, then Px has to divide Gx and Gx has to divide Px, and they are of the same degree. Yeah, and Px degree Px equals degree Gx. So maybe just one division is enough. Gx, which implies since both are monic, then it has to be same. Yeah, and monic. Maybe write this way: Px Gx monic, and degree is same. Hence, Px equals Gx. Yeah, so two polynomials which are of the same degree, monic polynomials of the same degree, and one divides other. That means they are the same polynomial, right? And of course, 2 is also immediate because this minimal polynomial. So now there is a unique minimal polynomial, and the minimal polynomial, of course, divides characteristic polynomial because characteristic polynomial satisfy this equation. Yeah, by Cayley-Hamilton. So there's maybe 2. So this is 1 and 2 by above and Cayley-Hamilton. Okay. So now let's look at some examples. Yeah, so can you give me an example of a matrix whose minimal polynomial and characteristic polynomial are same? Meaning a bigger 2 by 2 matrix, let's say. 1 by 1, of course, both will be same, but maybe 2 by 2.
The diagonal matrix 2003.
2003. So what is the characteristic polynomial of this?
T minus 2 into T minus 3.
And what is the minimal polynomial?
T minus 2 into T minus 3.
So it's the same, right? I wanted different. Oh yeah, this I told you to give me the same. Yeah. Yeah, so as you see, characteristic polynomial and minimal polynomial may have same degree. For instance, the roots, if the roots are distinct. So we will see that, so we already know that every root of the minimal polynomial will be a root of the characteristic polynomial. We will see the other side as well. Yeah, every root of the characteristic polynomial will be a root of the minimal polynomial. In other words, every eigenvalue of the matrix will be a root of the minimal polynomial. So to compute eigenvalues, you can use even the minimal polynomial if you have a way of computing. Okay. What about the other example where minimal polynomial and characteristic polynomial are different? Can you give me an example? Yeah, go ahead. What's an example? Maybe I didn't hear someone. Scalar, someone wrote scalar matrix. Abdul. Yeah. So yeah, so you can take any scalar matrix. Yeah. So for instance, you can take A to be the identity matrix. Okay. And then what is the characteristic polynomial? Is t minus 1 whole square. And what is the minimal polynomial of the identity matrix?
T minus 1.
T minus 1. Yeah. Because I mean, the minimal polynomial has to have degree at least 1, and this A satisfies it. Yeah. So the easiest way to see that it is a minimal polynomial. Okay. So we see that the roots are same, and we got a minimal polynomial different from the characteristic polynomial. So so if we take the root same, do we always get minimal polynomial same as the characteristic polynomial? So 2 by 2 matrix. Can you give me an example of a matrix which has the same roots, but maybe minimal polynomial not same as the characteristic polynomial?
1101.
Yeah. So if, for instance, the right thing to do is look at this. Yeah. And what is the the characteristic polynomial will not change. Yeah, it just depends upon the diagonal entries. Trying to compute some determinant. Yeah. So for upper triangular matrix is straightforward. But what is the minimal polynomial now?
Same as characteristic polynomial.
So it's not degree, at least it's not t minus 1, that we know, right? Because if we take t minus 1 and put in a, it doesn't become 0. And of course, so it has to, and it, I mean, it can't, it has to divide the characteristic polynomial, yeah, by the previous quality. So it has to be either t minus 1 or t minus 1 whole square. There is no other possibility. So it has to be t minus 1 whole square. Yeah. So, and you can see that it does satisfy. Yeah. So if you subtract from A identity, then you get 0. So A is, I mean, anyways, the characteristic polynomial, but more specifically, it's this square. Yeah. Which is the 0 matrix. Okay, so this is so all. So it's not. So if the roots are distinct, roots of the characteristic polynomial are distinct, then the minimal polynomial and the characteristic polynomial must be same. And then if the roots are not distinct, then it can have, everything is possible. I mean, the minimal polynomial may have a smaller degree, but it can also have the same degree as the characteristic polynomial, depending upon how these Jordan blocks look like. So we'll do Jordan form, and looking at the Jordan form, you can decide what the minimal polynomial is going to be. Okay, so if you can compute the Jordan form, whatever Jordan form is, then so we'll come to it in a bit. Yeah, but let's just study a little more about minimal polynomial before we get to. Okay, so first thing which I promised you is that if a lambda is an eigenvalue of A, then PA lambda is 0. Okay, if and only if PA lambda is 0. So one direction if part is okay, yeah, because if PA lambda is 0, then that tells you that characteristic A lambda is 0 because PA lambda divides characteristic A lambda. So PA means the minimal polynomial. So our notation for minimal polynomial is going to be P sub A, which implies lambda is an eigenvalue of A. Yeah. So that direction is fine. Now we have to do the converse. So now we assume that lambda is an eigenvalue of A, and we want to, that means characteristic polynomial CHA lambda is 0, and we want to show that PA lambda is 0. Yeah, that is what we want to do. So lambda is an eigenvalue means what? Means this, how do we compute characteristic polynomial? Look at lambda I minus A and compute its determinant, and that must be 0. Yeah. So that means this matrix lambda I minus A must be singular. Yeah, we want the determinant to be 0, which is same as saying that lambda I minus A is singular. Is that okay? Yeah. So lambda is an eigenvalue of A is equivalent to saying that lambda I minus A is singular. So now let fx be some polynomial. Yeah. For instance, we'll put fx to be the minimal polynomial. So say it looks like an x power n, an minus 1, x power n minus 1 plus a0. And let's try to compute f lambda I minus fa. Okay. So this is some linear operator. Yeah. F lambda is some number, you multiply by I, and then fa is going to be, you just plug in an times a power n, an minus 1 times a power n minus 1, and so on up to a0i. Yeah. So if you take the difference, what do we get? An. So here we have I, right? So I've just clubbed in together. So an lambda power n I minus a power n. Yeah, plus an minus 1 lambda power n minus 1 I minus a power n minus 1. Yeah, so if this is our polynomial, then this is what up to a1 we'll get lambda I minus a. And of course, the a0 term will not be there, right? Because f lambda, the a0 term, the coefficient is going to be I minus I, which is 0. Yeah. Is that okay? This equation star is clear? So now we simplify. So the point is we can factor out a lambda I minus a from each of these terms. So I've done it for the first term. So you factor out lambda I minus a, then you get this this polynomial. It's like x power n minus y power n. Yeah. So you just so if you multiply it through, you'll get that. Yeah. There will be a telescoping series. There will be cancellation, and you'll get this. Yeah, so you can factor out a lambda I minus a from the first term. Similarly, from the second term, and then you will get some matrix. From the third term, and you'll get some matrix, and so on. And the last term, we already have lambda I minus a. Yeah. So then we can factor out a lambda I minus a completely, and we'll get some matrix C, which we don't know what it looks like, but it's some matrix, yeah, some square matrix, which we don't care about as well. Okay. But the upshot of all this calculation is that f lambda I minus fa is a multiple of lambda I minus a, so it can't be non-singular, right? Because lambda I minus a is singular, the determinant of f lambda I minus fa is going to be 0, right? Because the determinant of lambda I minus a is 0, irrespective of what c is. Yeah, even if c is non-singular, it is its determinant. I mean, determinant of ab is same as determinant of a times determinant of b. So this is singular, which tells us, so what we have shown is that basically f lambda is the eigenvalue of fa. That is what we have shown. Yeah. But anyway, that is immaterial. So this is singular. So in particular, we can put f to be pa, yeah, the minimal polynomial. So what does that give us? Pa lambda I minus pa is singular. Yeah. But PAA we know is 0 because it's the minimal polynomial. So that tells you that PA lambda times I is singular. When is such a matrix singular? It's a scalar matrix, right? So it's singular only if it is the 0 matrix, yeah? Only if PA lambda is 0. If it's non-zero, then its determinant will be nth power of that element. Yeah? So that tells you that PA lambda is 0. Is that okay? So any questions? No? All good? Okay. So we see that minimal polynomial and characteristic polynomial have same roots, but it may happen that the minimal polynomial has smaller degree. Yeah. But it may also happen that it doesn't have a smaller degree. So keep these three examples in mind, and then there is a little chance of making mistakes if you keep these three examples in mind. Three examples on the left, which I hope is still visible. Now, we saw that the characteristic polynomial only depends upon the linear map. Yeah, it doesn't depend upon the choice of the basis. So you define it using a choice of a basis using this matrix, but it depends only on the linear map. Similar, that means if two matrices are similar, they have the same characteristic polynomial. So the same is true for minimal polynomial as well. If A, B, and are similar matrix, then PA equals PB. And the proof is straightforward as well. So since A and B are similar matrix, you can find a P such that B is P inverse AP, and then you just compute PAB. Yeah. So PAB is just P inverse PAAP. Yeah, because the point is P inverse. So how do you'll have to plug in B, right? B power n you'll have to. So PA is some polynomial. So it's B power n plus an minus 1, B power n minus 1. But B looks like P inverse AP whole power n. Yeah. So this whole power n is same as P inverse A power n P. Yeah. Because this, if you write I mean P inverse AP times P inverse AP. So the middle P's cancel out. Yeah. So you get P inverse A square P. Yeah. So this is what I'm using essentially. Right. So you do this n times and you'll get this. So, and then even for sums, it's okay. Yeah. So P inverse A P plus P inverse B P is same as P inverse A plus B P. Yeah. So you get this identity. Is this identity okay? Yeah. And of course, then you get that PAB is 0. Right. So that tells you that since PAB is 0, that tells you that the minimal polynomial of B must divide the minimal polynomial of A. Yeah, because of the result which we proved, the first result which we proved today. Yeah. So PBX divides PAX, because PBX divides every polynomial which is satisfied by B. Yeah. And similarly, so once you have PBX divides PAX, you can interchange. Yeah. So similarly, you'll get PAX divides PBX. and hence they are same. Is that okay? So it doesn't matter which. So two similar matrices have the same minimal polynomials. Yeah. Any questions or comments?
Sir, can you hear me?
Say that again.
Am I audible?
Yeah.
Sir, can you explain the second step once more?
Which step? Why PBX divides PAX?
No, sir. P of B is equal to P inverse P of A into P.
Yeah, sure. So you get this, right? P inverse AP whole power n is P inverse A power n P. Yeah. So okay. So maybe yeah. So the point is, what is PA? What is oh, I can't write. Let me see. Yeah, it's not allowing me to write. 1 second. Let me try to restart this. Right now, I was able to write. I wrote a few things. Yeah?
B is equal to P inverse A P. B square is equal to P inverse A P. And so on. All right. And also,
Yeah. So what does PAB look like? Yeah. So PAB. I'm not able to write again.
P plus B square, so we have is equal to P inverse A plus H square And so, like, for a polynomial, we can still write it again. Suppose we have one more polynomial of A to B, A1, A0 plus A1, H plus A1, blah, blah, blah. Similarly, we write for these polynomial. That's it. Can you see the screen?
Pen issue or something.
Sir?
Yes.
It's clear now, sir. You can continue.
Yeah. I can. Okay. But it may be some pen issue. That's why I can't write it.
Sir, I think the problem is you didn't click the hand icon there.
No, that is not required for the pen. But now I can write again. It's okay. So, yeah. So now it is clear, right? Basically.
Yes, sir.
Yeah, I still can't write. But anyway, now it is clear, right? So basically you plug in, you write down the polynomial explicitly and put B, and then replace B by P inverse AP in that expression. And then you'll get this, okay? So, but I'll have to write, so maybe let's see. Yeah, eventually we'll find a way. Let's go until I don't need to write, yeah? So let AB be two matrices such that A times B is a square matrix, yeah? So A and B need not be square, but A times B must be square. So once you know that A times B is square, B times A will also be square matrix, okay? Let alpha be a non-zero eigenvalue of AB, yeah? So it's an eigenvalue, but not zero eigenvalue, non-zero eigenvalue. Then what you can say is alpha is also an eigenvalue of BA, the other matrix BA, yeah? So some tricky kind of statement it looks like. And moreover, the dimension of the eigenspaces are also same. Okay. So you can, say it may happen that AB is some 2 by 2 matrix and BA is some 50 by 50 matrix. Yeah. If you start by with a 2 by 50 and 50 by 2 matrix, then it may happen that way. But what it's saying is that for non-zero eigenvalues, the dimension of the eigenspaces are same. Yeah, so the only change which can happen is for the zero eigenvalue. Okay, so it may, I mean, of course, it can't be true for all eigenvalues, right? Because the sum of the dimension of the eigenspaces must be the whole of sort of, I mean, so in the diagonal case, for instance, the diagonalizable case, sum of the dimension of the eigenspaces must be the whole of the dimension of vector space. Yeah. So the only change can happen only for the zero eigenvalue. That is what the theorem says. Okay, so let's try to see a proof. It's not that difficult. This is also not very difficult. So you start with a basis of the. So let's say alpha is an eigenvalue of AB, and let V1 to Vk be a basis of eigenspace of alpha for the matrix AB. Okay. So what does that mean? It means that ABVI is equal to alpha VI for all I between 1 to k, and V1 to Vk is linearly independent. Yeah, these are the things it means. Yeah. So now you multiply B on both the side on the left hand sides of this equation on both the sides. Yeah, so you pre-multiply by B to this equation. Then you get BABVI, and alpha is anyway a number, so you can pull it out, is same as alpha times BVI. Yeah. So now it looks nice. So BVI is a vector and BA is a matrix. So BVI is looks like an eigenvector of BA, right? And so as long as BVI is non-zero, then so eigenvector means it should be non-zero vector such that V is same as alpha V. Yeah, so that is the definition of eigenvector. So all we have to check is BVI is non-zero. Then we know that alpha is also an eigenvalue of our BA. But BVI is BVI is non-zero because alpha is non-zero, right? I mean, the first if alpha was I mean, if BY, say BVI is zero, yeah, then what does that mean? That means that BVI is zero. Then look at the first equation. Yeah, that means A times BVI is zero, which means alpha VI is a non-zero vector, so alpha must be zero. Yeah, VI, in fact, VI form a basis, right? So that will enforce that alpha is zero. Yeah. So since alpha is non-zero, BVI must be non-zero. Yeah, because ABVI is non-zero, right? So that tells you that BVI is non-zero. So that in particular, we have proved that alpha is a eigenvector of BA. Yeah. Now we want to prove that they have the same dimension. Yeah. So we know that BVI is eigenvector. In fact, we know that BV1, BV2, VK, they are all going to be eigenvector of BA with respect to alpha. Yeah, because I mean we didn't really. It doesn't matter which I we choose. Yeah. So in fact, the claim is that this whole set BV1 to VK is linearly independent. Yeah. And once we prove that this is linearly independent, it will tell you that the eigenspace of BA with alpha has dimension at least k. Yeah. And similarly, we can by symmetry we'll get the eigenspace of AB with alpha. So we'll get one inequality, and then the other inequality is by symmetry. Yeah. So let's try to see why it is linearly independent. So suppose there is a linear relation. Yeah, so suppose summation I equals 1 to k ai bvi is 0 for some ai's in your field F. Yeah. Then what you do, you apply a to it. Yeah, you have that is what we can do. Yeah, because we know what abvi looks like. So you multiply by a on the left, and you get this new equation. But abvi we know what it is. What is ABVI? It's just alpha times VI, right? Because VIs are eigenvalues, eigenvectors with eigenvalue alpha, same eigenvalue alpha. So we can pull out the alpha as well. Yeah, so we get this is same as alpha times summation AI VI is 0. Yeah, but alpha was non-zero. Yeah, so that tells you that summation ai vi is zero, and hence but vi's were linearly independent, so that tells you that ai's must be zero. Okay, so that completes the proof of the claim that this is linearly independent. Yeah, is that okay? And hence, as we argued, that the eigenspace dimension of AB alpha of alpha with respect to AB is less than equal to eigenspace dimension of B alpha. Yeah, because I mean this dimension is at least k. That was k, and this is at least k. So and then by symmetry, we get the other inequality. So you start with BA and the eigenvectors of BA with eigenvalue alpha, basis of the eigenspace, and do the same thing, and you'll get the other inequality. Okay?
Yes.
Any questions or comments? No? Okay. So we have done this as well. So these are some. So maybe one more fact, and then we will get to Jordan forms. So so how do you compute eigenvectors? So I mean eigenvalues you can compute by looking at characteristic polynomial and so on. Yeah, and then factoring. If you can factor that's it. But how do you compute eigenvectors? So this proposition will tell you a way to find an eigenvector. Yeah. So I don't know how you. So it may not be so easy many times, but but at least you can write a program. So manually it may not be easy, but by way of program you can probably try to do this. Yeah, find an eigenvector. But of course there are other techniques too. So for that you'll have to take a course on numerical analysis or something to figure ways to find eigenvectors and so. So let V be a non-zero vector in Cn or Fn, where F is some algebraically closed field. Yeah. So all we care is F is algebraically closed. So you can take Cn if or Fn as so because we want to have an eigenvector. Yeah. So for that we need an eigenvalue at least. We know that over Rn we may not have any eigenvector. The rotation, for instance, R2, the rotation doesn't have any eigenvector. So we need an algebraically closed. Let A be an n cross n matrix, then the set, or then the subspace, let's say V, AV, A square V, etc. So you start with V, apply A to it, apply A square to it. So you'll get a bunch of vectors. Yeah. You look at the subspace generated by that contains an eigenvector of it. That is what the proposition says. Okay. So what is the proof? So you take k to be smallest such that this is linearly independent. Yeah. So for instance, if AV is dependent on V, then you just take it to be V to be. So you don't have to take anything. Yeah, you just have to take V. Yeah. AV is dependent on V. That means V is already an eigenvector. Yeah. If not, then you take a square v. If a and av are linear, then you take a square v. Now a square v is dependent on a and av, then you stop at a square v. Yeah. Yeah. So in the first case, you will have to take v and av. In the second case, you take up to a square v and so on. Yeah. So since this is linearly dependent, you can find ai such that summation I equals 0 to k ai little ai times a power iv is 0. Yeah, this is the definition of linear dependent. So ais are complex numbers or in your base field f, whatever situation you are in. And what can we say about ak? Ak must be non-zero. Why? Why should ak be non-zero? Why should the last term be non-zero? what happens if AK is 0? What will you get?
If AK is 0, then we'll get all the other AIs equal to 0 since
this is K is the smallest with this property, yeah. So we'll get that see V AV A square V up to A power K minus 1 V is linearly independent, right? That is what we know from the choice of K. So all the AIs will be 0, and it will. I mean, that will somehow force that say that these are linearly dependent, linearly independent. Yeah. So AK must be non-zero. Yeah, because we know that some AI must be zero, non-zero, but we can in fact say that AK must be non-zero. Yeah. So AK is non-zero. Now look at this polynomial. Fx to be ai times x power I. Yeah. So this AI is same as the AI above chosen. Yeah. So look at this polynomial. This, of course, is a polynomial of degree k, right? Because ak is non-zero. So this is a polynomial of degree k. So you can factor it over an algebraically closed field, or over C, or any general algebraically closed field. You can factor it as product of linear terms into k factors. Yeah. So I mean, it may have repeated roots. That I'm not saying that alpha 1 to alpha k has to be distinct. Just that it will have k linear factors. So for now I am able to write. Good, right timing. Yeah. So for alpha I in C, or in, so we are not asserting that alpha i's are distinct. Now you look at gx to be, so you drop one of the alpha i's. For instance, you can drop alpha 1. Yeah. And look at this polynomial gx to be product of x minus alpha I. So gx is basically fx divided by x minus alpha 1. Yeah. So gx is also a polynomial with coefficient in f or c. And look at w to be g of a times b. Yeah. So w is going to be this vector g of a times b. Okay. So look at g of a times b. This is how does this look like? So g of a is a polynomial of degree k minus 1, right? So if you plug in g of a, what do you get? It's is some linear combination of v plus v av a square v and so on up to a power k minus 1 v. Yeah. Gav. Yeah. So maybe I can write it. Since and GAV is some linear. GA is G is a polynomial of order of order degree k minus 1. So GAV will be a linear combination of. So it will be B1 B plus B2 AV plus BK minus 1 A power KV. A power k minus 1b. Yeah, so this is what it will look like. But we know that v, av, ak minus 1, v are linearly independent. Yeah. So no matter what bi's are, this cannot be 0, right? Unless b itself, all the bi's are 0. But that's not possible because we know that g is not the 0 polynomial. It's a polynomial of degree k minus 1. Yeah. So in particular, we know that bk minus 1 is non-zero. Bk minus 1 non-zero because it's a polynomial of degree k minus 1. Okay. So that so we got a vector w which is non-zero, ga times v. Is that okay, everyone? So now I'm trying to say, so now we will show that W is in fact a eigenvector of A with eigenvalue alpha 1. Yeah. So what happens is you look at A minus alpha 1 I. Yeah. And if you apply it to W, so what is this? Okay, so maybe I've jumped a step. So this is maybe this is A minus alpha 1 I times GA times V. Yeah, this is what it looks like. But A minus alpha 1 I if, times GA times G of A times V is same as FA times V, right? Because X minus alpha 1 is the only factor missing from GX. Yeah, so if you multiply that, then you get FX. And then you are plugging in, yeah, A. So you get that this is same as FA, which is FA times V, but FA times V is 0 by this identity. Yeah, so so this is 0 by star. Yeah, so star tells us that FA times V is 0. So that tells you that, so I mean, this is how you figure out the eigenvectors, yeah? Or in other words, you expand it, AW is same as alpha 1 W, yeah? So that tells you that W is an eigenvector of A. W was a non-zero vector and A times W is alpha 1 times W, that tells you that W is an eigenvector. W is an alpha 1 eigenvector of. Yeah, any questions? Make sense, everyone? In fact, so if you want to get an alpha 2 eigenvector, what will you do?
You take G of X is the product of factors other than X minus alpha 2.
Yeah, so you just, instead of dividing by X minus alpha 1, you just divide by X minus alpha 2 and get the polynomial Gx, yeah? So you can get any eigenvector, eigenvector with any eigenvalue and with this method, yeah? Alpha 1 is just, yeah, so it depends upon which factor you divide by and you get that eigenvector. Yeah, so someone. Yeah, give me a second. Up to I'll come in. I'll tell you what is it. Hi. Yeah. So, what do you want me to explain? Which proof? Which this proof you want me to explain again? You can speak. Yeah. There's. Say that again. Your volume is a bit low.
So he wants you to explain from the f of x part.
Okay. Let's see. Yeah. So you consider this polynomial fx is ai times x power I, yeah, where ai's are these entries. Ai is the coefficient of a power iv, yeah. So if you look at this, this is a polynomial of degree k because ak is non-zero, yeah. So basically, I mean, if you want to visualize it, it is ak x power k plus ak minus 1 x power k minus 1 if you want to write it in like a usual polynomial plus a0. Yeah. So ak is non-zero. So it's a degree k polynomial. And now since you are over a algebraically closed field, you can factor it. You can write it as x minus alpha 1 up to x minus alpha k. Okay. So this you can even work out in a more general setup as long as field has the property, this polynomial has one root, then also you can figure you can find out the eigenvector. But let's say over algebraically closed field, you can factor it like this. then gx is basically fx minus. So another way to think of gx is fx over x minus alpha 1. Yeah. So gx is another polynomial. You're just dividing out one of the factor. It's another polynomial with coefficient in the complex numbers, field of complex numbers. Yeah. And then what do? So gx will look something like this. Yeah. So maybe I'll use this. So maybe this should be b0 and this should be b1. So this is a polynomial of degree k minus 1. So it will look like b1x plus b0. Yeah. So this is how it looks like. Yeah. So what is w? W is you just plug in these plug in a for a for x in the expression of g and then multiply by v at the end. Yeah. So if you do that, then this is b0 I times v, b1 a times v, bk minus 1, a power k minus 1 times v. Yeah. So here I've written in the reverse order, but that's the only difference. Is that okay, Abdu? Okay. So now, so what we get is that this is a non-zero vector because this can't be zero. I mean, the vectors a power k minus v are all linearly independent by the choice of k. Yeah, k was the smallest such that this is linearly dependent. So since they are linearly independent and bk minus 1 is non-zero, this must be a non-zero vector. Okay, so you get that W is a non-zero vector, and now you multiply by a minus alpha 1 I to W. Yeah, and then that is same as a minus alpha 1 times G times GA times V. Yeah, because W is just GA times V. So we are replacing W by GA times V. But a minus alpha 1 time I times GA is same as FA. Yeah, because fx is same as x minus alpha 1 times gx. Yeah. So you get that, and fa of v is of course 0 by this star, right? This is how we got this polynomial f using this star. Yeah, so f of a times v is obviously 0. So that tells you that. So once you have that a minus alpha 1 I times w is 0, you get that aw is equal to alpha 1 w. Is that okay? Okay. So that completes the proof of this fact that if you consider this set, the span of V, A, V, A square V, and so on, then it must contain a eigenvector. Okay. So now let's talk about Jordan forms. Okay. So have you seen what? Do you know what Jordan forms are? Okay. Again, I'm not able to write. Do you know what Jordan forms are? Anyone? None of you know. Okay. Then one should do it slowly. Yeah, so it's good that I haven't written. But I'm not able to write now. It's just about writing everything, okay? So what should I do? Yeah, so I use this because it's easier to sort of maintain the notes. And I've been, or maybe because I've been using it for a long time since COVID. So, okay. So let me restart and hopefully then, okay, let's see if I can write somewhere else. don't know what's wrong today. This pen. Yeah, now I can write. Okay, so sometimes you have to do things so that the pen remembers that it's supposed to write. So let's see. So um, what is, yeah, it's working. What is the Jordan form of a matrix? Yeah, so it makes sense only when you're working over a algebraically closed field. Yeah. So if you have a matrix with some entries, then the Jordan form. Yeah. So the Jordan form makes sense only if you are working over algebra, because you want all the eigenvalues and so on. Yeah. So let A be a n cross n matrix. Okay. Then, so maybe this is, you can think of it as a theorem, whose proof we will give in a bit. Or maybe, I don't know, what time is it? 12:16. Yeah, so maybe not the complete proof. I'll start the proof because I don't want to go too far. So let A be a n cross n matrix. Then uh, there exists a matrix. Basically, it's similar to something which is called the Jordan form. There exists a matrix P such that P inverse AP looks like, yeah, so now we should write down a big block matrix, yeah. J1, or rather J lambda 1, J lambda 2, J lambda n. Entries over F. Yeah. So then there exists a matrix P such that P inverse AP looks like this block matrix, and the rest is zero, where J lambda I is, so this has a very nice structure as well. So it will look like lambda 1 to lambda I. So on the diagonals, it will be lambda I. So depending upon what the size of this matrix is, so maybe let's say K, then and the just above the diagonal, it will be ones. So, and then the rest is zero. So this is all ones, and I one, the next entry is one, and so on. And the, so it's an upper triangular matrix with this kind of thing, yeah, where so yeah, maybe I can stop here. So maybe it looks like this, yeah. So that's it, where lambda is are in F.
So,
Yes.
so in the matrix, it doesn't need to be J after J lambda n, right? Because if it is after J lambda n, for it to be an n cross n matrix.
Yeah, J lambda m, that is right. So we start with a n cross n matrix, then there may be lambda 1 to lambda m, so many guys, and the each lambda and maybe J lambda I, let's say, is of some size, yeah. J lambda I is, it will depend on I. So let's call this Ki cross Ki matrix. Yeah. So what we have is that summation Ki I equals 1 to m is n. Yeah. So this is something which you can say. Yeah, the relation between m and n, ki is n. Yeah. So once you have this is called the Jordan form of A. Yeah. This is the Jordan form. This is the Jordan form of A. So of course, it is not clear how you get this, yeah. But assuming you get it, yeah. So suppose you know that you can see, you know this theorem, yeah. Then what can you say about the eigenvectors, eigenvalues of A? What are the eigenvalues of A? Give me a second, yeah. Yeah. So what can you say about the eigenvalues of A? Yeah, tell me. I mean, this is not something too much to ponder about. Yeah. What are the lambda eigenvalues of A? Yeah, so it is this eigen. So it is lambda 1 to lambda m. Yeah, right. Because B, this matrix B, which is this Jordan form, and A will have the same eigenvalues. They are similar, right? And for B, we know that it's an upper triangular matrix, right? So the diagonal entries are going to be the eigenvalues, and the diagonal entries are precisely lambda. For J lambda 1, it is precisely lambda 1. For J lambda 2, it is lambda 2, and so on. Yeah. So that tells you that lambda 1 to lambda m are indeed. So from Jordan form, you can. Yeah, give me a second. There's some call. Yeah. So now uh, lambda 1 to lambda m are indeed the eigenvalues, and because B and A has the same eigenvalue. Yeah. Can you guess the? Okay. So that may be even more difficult. So let's see. Um, let's look at J lambda 1. Yeah. So let's say J lambda. J lambda looks like this matrix. Yeah. Lambdas, bunch of lambdas, and 1 at these entries in this. Yeah. So let's just concentrate on J lambda. So what is the minimal polynomial of J lambda? Yeah.
It will depend on the size of Jordan block. Then lambda dot k will be the minimal polynomial.
So suppose it's K by K. Yeah. K by K matrix. Then what will be the minimal polynomial? What will be the minimal polynomial? So it has to have factor x minus lambda, yeah? And what is it? So of course it's not x minus lambda, yeah, because if it is k is greater than 2, then x minus lambda is not, I mean, if you plug in j lambda here, you won't get 0. So what do you have to do? So someone answered something, yeah, just repeat it.
The T minus
I can't hear clearly. Can you speak it louder?
I think in chat.
I still can't hear properly. Okay, so Amarga wrote, so it was maybe Amarga, yeah. So it's yeah. So in this case, since I've written x instead of t, so x minus lambda power k, yeah. So if you see that if you raise it to, if you square it, then these ones will move a little above, yeah. So maybe you can try to do this exercise. So it's 0, 0, 0. So maybe let's say 4 zeros, yeah. So this. So 3 ones, and then 0, 0, and then 0, and here 0. So if you square it, you will see that what will happen is this ones will move a little. So you'll get 0, 0, 0, and then 1, 0, 1, and then it will stay upper triangular. And then if you cube it, then one will yeah, so you'll have to raise it to the 4th power to make it. So if you cube it, the one will go to this this position, and if you so so you'll see that cube it, then there will be a 1 in the last no, and in the top right corner, and if you do the 4th power, then you'll get 0. Okay, so this is something which you can do by hand, multiplying by hand. Okay. So that so this is true more generally. So if you do k minus 1th power, then it will not become 0. Yeah. To make it 0, you'll have to take the kth power, and then only it will become 0. Okay. So the minimal polynomial in this case is yeah. So what I have written, yeah. So this is true. So this is how the Jordan blocks look like. Yeah. Now here the lambdas may not all be distinct. Yeah. So there may be repetition. Okay. So for instance, so it may happen that lambda 1 is same as lambda 2 is same as lambda 3. Yeah. So so maybe before doing the proof, let's see some example of Jordan forms of some matrices. Okay. So yeah, so maybe let's look at these 3 examples. So they are more or less in Jordan form. So but maybe let's try to make it consistent with our notation there. Yeah, this thing. Okay. So or maybe instead of writing here, it might be a little bit complicated to present it in the notes. So let's write there itself. But we know what the matrices are. Yeah. So let me just do it here itself. Yeah. So examples. So for instance, the first example was 2, 3, 0, 0. Yeah. So is it in Jordan form? Yeah, so this is in Jordan form. So there is J2 and J3. Yeah, there are 2 eigenvalues, and there are 2 blocks. J2 and J3, and both J2 and J3 are of the size 1 cross 1. Yeah. So this is in Jordan block. The other one was the identity matrix. Yeah. So it is in Jordan form, but the Jordan form is basically so maybe I'll write it this way: J2. How about this one? If I want to write it as in Jordan form, how does it look like? So maybe one should put what is the order of the matrix here. Yeah. So J11, J21, and J31. Yeah. So then the notation will be sort of complete. So let's call this Ki to signify that this is K by K matrix. Yeah. So lambda and K determines the whole Jordan block. Yeah. So if I want to write identity as in Jordan form, so what are the Jordan blocks? J1, and what is the size of the block? So this one is J11, J11. Yeah. So it is again in Jordan form, but it's not, I mean, though the eigenvalue, so here the two lambda 1 and lambda 2 are same. Yeah. So this is how, and then of course 0, 0. Yeah. So this is how it looks like. Yeah. And what about this one? So this you can see is J12, right? So it has only one Jordan block. Okay. So the other two examples had two Jordan block, but this had only one Jordan block. Yeah. And if you do more complicated matrix, you can get more complicated Jordan forms and so on. So the objective is, if I give you any matrix, you try to get it into a Jordan form. So if you have matrix in real numbers or something, you assume it is complex numbers, and you try to write it in the Jordan form. So the point is, these lambda i's may not exist on the field of definition. So if your matrix is in F, the eigenvalues may not be in F. Yeah, you may have to go to algebraic closure to get the eigenvalues. And then of course these entries of the matrix P may not again be in the field. Yeah, this P may not be in the field. So if you are over algebraically closed field, then you can always make it into a matrix of this form. That is what the theorem says. Okay. So there is a proof of this theorem using, so there is a more canonical proof using structure theorem of PID, structure theorem of finitely generated modules over a PID, which is same as structure theorem of finitely generated abelian groups. So you may have heard of structure theorem of finitely generated abelian groups. Have you? Yeah. So there is a similar theorem for structure theorem for finitely generated modules over PID. So those who know modules will know what it means. But say a similar theorem and similar proof. Yeah. So there is no, except for the definition of what a PID is, what a module is, the rest of the proof goes through in the same way. Okay, so the ideas are not new, just and using that theorem one can prove this. But since we are not going to do the structure theorem, I'll give you a different proof. Yeah, which is slightly on the tricky side, but anyway, you'll have to do something. Yeah, either learn some abstraction, or do a different proof. Okay. So I'll not give you a proof completely, but maybe I'll introduce something called the generalized eigenvector. Yeah, and then maybe we'll close it Or maybe let's stop here. So maybe I'll do even the generalized eigenvector next time, because I'll have to recollect anyway. But maybe you should try out some matrices. Yeah. So if I give you something like, so maybe let's say 3 by 3 matrix. Yeah. So another example. So this was 1, 2, and 3, and let's say this is 4. So it's a 3 by 3 matrix. 0, 1, 0. Yeah, so this is, I've written it in a more complicated way than I should write it. Yeah, so consider this matrix. Okay. So what do you think is the Jordan? So this is not in Jordan form, right? Because it's supposed to be 0 here in the corner. So what will be the Jordan form of this matrix? So instead of so what are the eigenvalues of this matrix? That we can figure out, right? Because the matrix is nice. So what are the eigenvalues? Is just 1. Yeah. So all the eigenvalues are 1. So uh, eigenvalues 1. Yeah. So once you know that the eigenvalues are 1, is 3 by 3 matrix, right? So there are only so many Jordan forms, yeah, possible. So Jordan forms, all the eigenvalues are 1, right? So there are only so many Jordan forms possible. So let's just list it down. Yeah. So one is J11, J11, J11. Yeah. Which of course is the identity matrix. Yeah. Is this possible? That the Jordan form of this is identity? What is the gut feeling? Is it possible? Come on, guys, just say yes, no. What is your feeling? You're not gonna lose $1 million, yeah? You just have to make a guess. How many of you think it's yes? Raise your hand, I can see that. Is this the Jordan form? No one thinks it. How many of you think it's no? Just raise your hand. Okay. Yeah, so at least the guess is on the right direction. So can you give me an argument why it is not?
Sir, then it will be the matrix is similar to the identity matrix, and then the matrix will be diagonalizable.
Uh-huh.
But here the minimal polynomial of the matrix will be t minus 1 whole square, and from this we can conclude that this matrix is not diagonalizable.
Exactly. Yeah, so you see that the minimal polynomial of this matrix, let's call this matrix A, yeah? So of course it's not lambda minus 1, yeah? Or it's not t minus 1, because if you subtract identity matrix to A, then it doesn't become 0, yeah? But the identity matrix has minimal polynomial t minus 1, yeah? So they can't be similar. The similar matrices have same minimal polynomial, right? In fact, we know that the minimal polynomial of this is t minus 1 whole square. Yeah. So PA, I mean, it has to be a factor of t minus 1 whole cube, and the only factors possible is t minus 1, t minus 1 whole square, t minus 1 whole cube. And you can check that t minus 1 whole square works. Yeah. So if you square the matrix 0, 0, 0, 0, all zeros except one in the off diagonal piece, 1 in the off diagonal, square it, you'll get 0. Yeah, so the minimal polynomial is this. So this is ruled out. Yeah. So other possibility is j 1 1 and j 1 2. Yeah. So this is a possibility. In fact, they do have, this also has the minimal polynomial. So the minimal polynomial of this matrix. So what does this look like? 1 and 0 0 0 0 and then 1 1 0 1. Yeah. So this is what it looks like. And if you square it, then you will see that it becomes 0. Yeah, because I mean, you do it to this diagonal block diagonal matrix. It's not 0, but if you, what I meant is if you subtract identity and then square it, then it will become 0. Yeah, because you do it to this block matrix. Yeah, and you'll see that you square. So J1, I mean, if you subtract 1, so if you subtract identity, so this minus identity is just 0 0 0 0 1 sorry 0 0 1 and then this is zeros. Yeah, so if you square it, you'll get 0. Yeah, so this has minimal polynomial e minimal polynomial, let's call this b. pbt is just t minus 1 whole square. Okay, so it is possible, right? And the third possibility, C, is that you have C is J13. Yeah, that is one another possibility. And of course, you can interchange these two blocks. So interchanging these two blocks, so you assume some ordering is there, yeah, so that you get some sort of uniqueness as well. But interchanging these blocks will still, I mean, you just have to conjugate it by some permutation matrix, then B and that interchanging these blocks is going to be similar to this thing, yeah. So what you do is in this case, so maybe I'll write it more precisely next time. In these Jordan blocks, you sort of order them by the block size. Yeah. So the bigger blocks come lower and the smaller blocks come upper. Then there will be uniqueness as well. Okay. So so of course C is not. What is the minimal polynomial of C? PCT. So this you can see is t minus 1 cubed. Yeah. So if it is J13, then you can't do it by square. You'll have to do cube. Okay. So so that tells you that this is our answer. Yeah, B is the answer. So you can compute the Jordan form of this matrix A is B without doing any manipulation. Yeah. So I'm meaning, ideally, if you want to do it, you'll have to do row operation, column operation, and so on. Yeah. So to compute a similar matrix, it looks quite. So of course, whenever you are trying to do all this similar to this thing, then you'll have to do a row operation and the corresponding column operation, and it's a mess. Yeah. So finding Jordan form in general is not so easy. Yeah, it's computationally more involved. But smaller matrix, you can play these kind of tricks, yeah, and compute the Jordan form of the matrix. Okay, so I'll assign some homeworks based on this so that you get accustomed to calculating Jordan forms for smaller matrix. For arbitrary matrix, it's not so easy. So one has to use a lot of theory and stuff. So it's involved work. Okay, but proving this result will not be that bad. Yeah, so I'll prove this that every matrix can be written in this form. Okay, so maybe we can stop here. Yeah, and for today.